So hello dear students, and I think today we have discussed in the classroom, we were discussing the potential barrier problem. And here I would like to have a discussion on, I would like to have some view on finite square well potential. And in case of finite well square potential, what we have is we have zero potential, and then there is dip in the potential. There's a sharp dip, and this dip is constant up to some length, and then uh, we're back to the track, and again we have the zero potential situation. And if we have to design this finite square, the talking about its potential, it has negative potential of magnitude minus v, and we can write down. So here, if we break down this potential in such a way that at this point we have minus a, and at this point we have plus a. So the negative potential is constant from minus a to plus a, and its value x less than minus a, the potential is zero, and the same thing is true with x greater than a, where the potential is zero. So potential is negative in this problem, and this constant negative potential extends from minus a to plus a. So to deal with this kind of problem, we would like to have, certainly we have three regions. We have region 1, we have region 2, and we have region 3. And we would like to write down the general solutions for these three regions, the general solutions of Schrodinger's equations for these three regions. And then we would like to apply the boundary conditions on this problem, because it's important for the eigenfunction to be continuous. So we will exploit the boundary conditions on this problem. And talking precisely, this problem can have both odd as well as even solutions, but we will track down this problem only with even solutions. And what we have the potential that's defined here. The potential is minus v for this x line between minus a and plus a, and otherwise this potential is zero. So it is zero with x less than minus a and x greater than a. So we can boil down it to the magnitude. So the magnitude of x greater than zero will give us it has zero potential connected with it. And this v is basically a positive constant, and this potential that we have chosen here, it admits both bound states. So what is bound state? The bound state is if the energy of the incident particles is less than zero, and the scattering state is when E is greater than zero. So so we have the region x less than minus a, and what we have here in this region 1 is that the potential is zero. So the particle has no interaction with the potential. So we can interpret this thing. I'd like to sketch another diagram for this. We have a situation like this. If I'll take it on the upper side, and this is my zero, and it's my zero potential. So there is sharp decrease in the potential at minus a, and there is sharp rise in the potential at plus a. So this is my plus a, and this is my region 1, this is my region 2, and this is my region 3, and this is my x. And we can write down Schrodinger's equation for this region 1, and we can write down minus h cross square by 2m d2 psi by dx2 is equal to E psi. So this will be This will be the first Schrödinger's equation for the region 1, and we can write down the solution for the Schrödinger's wave equation. As we understand that in region 1, the potential term is equal to 0. And we can write down the solution in such a way, say, let's take K1, K1 square is minus 2m E by H cross square. So this K1 is on the root of minus twice ME by H cross. So we have the Schrödinger's equation, and we can write down this this K1 as under root of minus 2m E by H cross. Now, in order to make this K1 a real number, it is important for E to be less than 0. So E has to be negative. So if E is negative, this K1 is a real number. So we have this K1, and if I write down the Schrödinger's equation again, what I have is I have d2 psi by dx2 plus K1 square psi equal to 0, where I have already written K1, which is under root of minus 2me by H cross. And what is true here is that E is less than 0. So E is negative, so that this K1 is real. So we have the Schrödinger's equation, and we can write down its solution as psi of x equal to a e to the power of minus K1x plus b e to the power of, so it has to be plus, and it has to be minus. So minus K1x. Now, I think let's choose this as minus and choose this as plus. Now, in doing so, we can see that this wave function, if this x is taken equal to, we can look for this what we call as the first term that we have chosen here, and this general solution for this differential equation, and we can see that the first term that we have, it banks at x equal to minus infinity, and it doesn't have any physical significance because it goes on infinity as x tends to infinity. So for that, this a, the constant that's associated with this term, this a has to be 0 in order to get it out of the solution of this problem. So the solution for this region of this potential well is b e to the power of K1 x, and that's true for x less than a. Now let's go with we have another region now. We have region from minus a to plus a. So we are interested in this region, and we would like to write down the Schrödinger's wave equation in the region. So what's that region? That region is it's the region from I should write the region from minus a to x to plus a, or in the short form we can write down the magnitude of x less or equal to a. Now in this case we have the Schrödinger's equation, that is E psi equals minus H cross square by 2m d2 psi by dx2 minus v of psi. So we can look at it again. We have a situation like this, okay, and we have this region, we have this region, and we have this region, and we can expect a situation like this where there is exponential rise, and then there is the combination of sine and cosine in the region 2, and then there is an exponential fall in the region 3. So keeping in view the mixture of sine and cosine, because this part is basically made of sines and cosines, we can look for the solution of this Schrödinger's equation, and we can write down its solution. And to write down its solution, what we have is we can boil down this like there we had chosen K1, so here I have K2. So k2 square of psi is minus d2 psi by dx2, where this k2 is under root of twice m e minus v. So this is e plus v divided by h cross. So I can think of writing the solution here for psi of x equal to c sine of k2x plus d cos of k2x. And so this is the solution for this Schrodinger's wave equation in the region from minus a to plus a. And although we understand that E is negative, and it's negative for the bound state, it's negative for this bound state, and certainly it must be greater than that of this V, this negative V that we have here. Its value should be greater than that of V, and in order that this L, that this K2 that we have here, this K2 has to be real and it has to be positive. Now, in that case, we have the solution, and solution is psi of x is c sine of K2x and d cos of K2x, where this C and D, these are basically the arbitrary constants as we have in the region 1. And finally, we have region third here. So this is our region third. This is our region 1. And for region third, we can write down the solution as for region 3. We have the solution for this Schrodinger's wave equation, that is f e to the power of minus k1x for x greater than a. So see, we have not taken another term for this solution because there is no reflection there's no possibility of any reflection in the region third here. So what is important now is that we have to impose the boundary conditions, and boundary conditions are quite evident. And what are the boundary conditions is that this psi, okay, again I would like to draw this this potential well, and this is at x equal to minus a, this is at x is equal to plus a, and and what is important here is that this wave function that we have been talking about, it has to be continuous at the boundary as it is, and it has to be continuous at both ends of this potential well, and so psi has to be continuous. That means the derivative of psi has to be continuous. It has to be continuous at x equal to minus a and x equal to plus a, and we would like to choose our potential. I mean, in this problem, we will choose our potential as the even function. So we choose the potential as even function. So so that we can assume the solution. We can assume the solution. We can assume solution either in even or odd forms. And always the advantage of this is that we need only to impose the boundary conditions on one side. And in this case, we will apply boundary conditions on the right side. I mean at x is equal to plus 1. And the other side that we have, x equal to minus 1, this other side is then automatically, you will have a situation like psi of minus x is equal to plus minus psi of x. And in this approach, we will choose only the even solution, and certainly the cosine term will exist because cos theta is an even function, and sine is an odd function. So we can write down the complete wave function for this problem as psi of x is, okay, let us start from the top, that is f e to the power of minus k1 x. This is for x greater than a. Then we will choose d cos of k2x for 0 less than x, 0 and a. And then by symmetry we can have psi of minus x so that x is less than a. And the continuity that we have in our problem, that is at x is equal to a. So if I go with the potential, so this is our a, x equal to a. So here we have a continuity, and we will say that then f e to the power of minus k1a must be equal to d cos of k2a at this point. And so for psi to be continuous, we have this equation. The derivative of psi at this point has also to be continuous. That means d psi by dx at x equal to a, it has to be continuous. So if it has to be continuous, what we will have is we will take the derivative, and what we'll get minus k1 f e to the power of minus k1 a is equal to minus k2 d e to the power, oh no, there's no e to the power, sine of k2a. And we can immediately divide these two equations. If we divide the two equations, we can see there will be cancellation. This will cancel with this, and we'll have d cancelled with this, and we will have sine theta by cos theta. It will give us something like tan theta. So we can proceed. We can proceed from here. So what we can do is dividing above equations. So when we divide these equations, what we will come up with is we will have k1 equal to k2 tangent of k2a. This is the result that we will obtain by dividing these two equations. It's a simple division between this and this. And so moving on from here, we can look for say I choose 1 by a under root of z naught square minus z square as the function of k2 tan of z. So how is this possible? This is possible if z is chosen equal to k2a and z naught is chosen as a by h cross under root of twice mv. And so what we are going to obtain from here is we can rearrange the terms, and we can obtain a parameter like z naught by z whole square minus 1 equals tan of z. So we have what we have here is we have tan of z equal to under root of z naught by z whole square minus 1, and all other correlations between the potential and z naught and z are here in above two equations. And this equation that we have in front of us, this is called transcendental equation. Transcendental equation. I have bad handwriting, I can't help it. And this transcendental equation defines the discrete energies which are allowed as stationary states, So we would like to have would like to have some discussion on this transcendental equation. But what is important here is that we have chosen the even solution. So we have chosen the even solutions to this potential well, and students can carry out the same exercise on the same problem, and they can choose for odd solutions, and they will reach to the same conclusion. But there will be some transportation of some of the points that we can expect. So what we do is we plot the graph. We plot the graph between tan of z, which is equal to under root of z naught by z whole square. So we choose an axis like this is my axis. So this is 2 pi. This is pi. And this is 3 pi by 2, and 2 pi, and 5 pi by 2, and this is my z that we have defined already. And then there is a plot, and we have what we have is we have a situation like this for we have this is and then we have z equal to, we'll choose z equal to, okay, this has to be pi by 2, and this is our 0, and then we have a curve for z equal to 0, z not equal to 0, and we have a curve for z not equal to 4, and we have a curve for z not equal to 8. So this is z not equal to 2, this is z not equal to 4, and this is z not equal to 8. So I would like to keep it like this. So this is this is the plot of the transcendental equation for Z, because we know that Z is very much connected with the energy. So when we are looking for Z, when we are plotting Z, we are plotting energy as a function of Z naught. And this equation, it can be solved numerically. It can be solved using computers, or we can use the graphical plotting. And I have tried to sketch the graphical results for this transcendental equation, and we can inspect some of the conclusions of special interest from the graph that we have plotted here. We have plotted it here with respect to what we call as this is our Z, and this is our tan of Z. Okay, so now if we look at this Z naught, this Z naught is very large. I mean, if this Z naught is large, here its large value is 8. What it does, it pushes the curve. It pushes the curve upward on the graph, and sliding the zero crossing and Z naught to the right. I mean, the intersection that we have between this line and this line, it occurs just slightly below what we define as Zn equal to n pi by 2, with this n being an odd number. Now, what it follows is that what do we expect here is we can translate down it in a very simplistic approach, and that is we have gone through the even solution approach. And what is Z basically? Z is nothing but K2A, and this is what? This is 2m times E plus V by H cross. Now we can see that this En, if I look for E and V, this is just the energy above the bottom of the well. E plus V is the energy above the bottom of the well, of whose width is the width is from minus A to plus A. So its width is 2A, and the even solutions approach those of the infinite square well for for the higher values. So what we expect here, we can see that for large z, we have for large z naught, the curve goes to the higher end, and for the small z naught, the curve goes to the smaller end, and this reflects this is the reflection of infinite Scarvel, and we have already discussed the infinite Scarvel, where particle has only some discrete energy states. So it must exactly behave, this Scarvel potential should exactly behave as a particle in an infinitely particle in a box which has infinite potential at its edges, for z naught equal to 8. So we can look for it. We can translate down this as, so for v tends to infinity, then this z naught also tends to infinity. So we can say that this zn, the nth of this z, it will be n pi by 2, where this n can have the values 1, 3, 5, and so on and so forth. So this n pi by 2a h cross will be nearly equal to under root of 2m en plus v naught, because there is a complete possibility of quantization of energy. So there will be discrete energy states for the particle. That's why instead of En has been incorporated here, and we can scatter it down on both sides. We'll have n square pi square by 4. It should be 4a square is nearly equal to 2m times En plus this is v. And so we can write down here, so 2m will come down, so we have En plus v equals n square pi square by 4a square. That is the case times 2m. So En plus v is nearly equal to n square pi square h cross square by 8ma square. This is the exact result that we have obtained for particle in a box. The particle in a box having infinite potential at its edges. So what we see here is what we suggest here is that this E plus V is the energy above the bottom of the well. And on the right side, what we have precisely the infinite Scarvel energies. So the graph that I have plotted here, on the right side of this, if we go on moving on and on, we will have a situation like infinite Scarvel problem for the well of whose width is of the order of 2a. So we can say here that the finite Scarvel goes over to infinite Scarvel as this v that we have chosen here, as this v tends to infinity. However, for any finite potential v, there are only finite number of bound states for the particle. And now there is another case, and the case is if this v that we have, where's the graph, the bad graph that I have drawn. Now, if this v, if this v tends to 0, okay, so if this v goes on the lower side, and obviously this z naught will go towards 0. So what we are expecting here, we are expecting that the number of states decrease. The number of states decrease until the lowest odd bound state vanishes. And however, the ground state, I mean the lowest even state, will never vanish. It will stay there. So there is always a bound state, no matter how shallow the well is. So the argument is that as this z decreases, there are fewer and fewer bound states until finally for this z naught equal to pi by 2, only 1 remains. It is interesting to note that however, that there is always one bound state. There's always one bound state, no matter how weak the well becomes. So this is till now we have been talking about the bound states of the given problem, in which the energy that we have chosen, the energy of the incident particles that we have chosen, is less than 0. Now, After this, we would like to go with the scattering problem. I mean, the scattering becomes prominent when this energy E is greater than zero. This E less than zero goes with bound states, or we may call them stationary states. And for E greater than zero, what we have E has to be the energy of the particles that are incident on this potential well. Their energy has to be greater than that of zero to the left. So so here we have clarity. This V of x is zero, and here we have a value, and here we have V of x equal to zero. So now looking for this. For this problem, when E is greater than zero. Now, simply if E is greater than zero, we are talking about the scattering of particles. And we are dealing with the same problem, and we can write down the solution. And solution for the first region, psi of x will be a e to the power of iota k, let me choose k1x plus b e to the power of minus iota kx. This is for x less than minus a, where this k1 is simply under root of twice me by h cross, because E is greater than zero. So this is K1. Now inside the well, what's the situation? V of x is V of x. We're taking it as V of x. So we will have psi of x equal to C sine of K2 of x plus D of cos K2 of x for the region minus a less than x less than a. And here we have K2 equal to under root of twice me plus V divided by h cross. And to the right, the third region that we have, for that psi of x will be f e to the power of iota k1x. Okay, so this is for the region 1, this is for the region 2, and this is for the region 3. So we can use the boundary conditions as we have used in the previous case, and there are 4 boundary conditions that we have. We have to have psi of x to be continuous, and d psi by dx at that point should also be continuous. These are 2 important parameters. So in doing so, what we will have is a e to the power of minus iota k1a plus b e to the power of iota k1a is equal to minus c sine, minus, it's equal to minus c sine of k2a plus d sine of k2a. Okay, so we will have for continuity, what is important is that d psi by dx should also be continuous. So in doing that, what we have to do, we have to take the differentiation of this, and we have to use the limit. We have to replace x by a. So using this boundary condition, what we obtain is iota k1 times a e to the power of minus iota k1a plus b e to the power of iota k1a is equal to k2 times c cos of k2a plus d sine of k2a. All right, so now we have continuity at minus a, and we have to have continuity at plus a. So these 2 equations are a result for the continuity at plus a, and similarly we will have another 2 equations for the continuity at minus a and plus a. So I can write down those equations. We will have c sine of k2a plus d cos of k2a is equal to f e to the power of iota k1a. And the last equation that we will have, because d psi by dx has to be continuous, we will have k2 times c cos of k2a minus d of sine K2A bracket equals iota K f e to the power of iota, this has to be k1, e to the power of iota k1a. So we have taken its derivative, so the exponential function remains as its, and you take the internal derivative of iota k1a, so that you have iota k1 here. The same thing goes here when you make such differentiations, and we can utilize the two equations, and we can use the phenomenon of elimination by substitution, and we can eliminate C and D in our equations, and solve the remaining two for B and F, and from that, this is a simple algebra. Students should work on it, and they should obtain the results, and the results that we obtain are B is equal to I sine of 2K2A divide by 2 K1 K2, then we have K2 square minus K1 square times F, and F comes out to be e to the power of minus twice I K1A, then we have A divided by cos of twice K2A minus I times K1 square plus K2 square divided by twice K1 K2, then sine of 2K2A. And from these two equations, we can calculate the transmission coefficient, and we can write down the transmission coefficient in terms of the original variables. So the transmission coefficient comes out to be t raised power minus 1 equals 1 plus v square by 4e times e plus v, then sine square of 2a by h cross under root of twice m e plus v times. And what we can notice in this equation is that this t is equal to 1, and it becomes 1, and the well that we have, it becomes transparent, and whenever there is this sign is 0, we can say that this t becomes 0. The value of this t comes out to be equal to 0, and we can have this thing equal to, so this sine of sine square of 2a by h cross under root of twice m by h cross times 2m times e plus v. This must be equal to sine square of n pi. So what we can obtain from this is we can obtain that this 2a by h cross under root of 2m times en plus v is equal to n pi, where this n that we have, this is any integer, and the energies for perfect transmission then should be given by, how can we write that? We can write down that en plus v is equal to n square pi square. This will go up, so this will become h cross square, and because we're doing squaring on both sides and getting v out, divided by 2m times 2a whole square, and which happens exactly like that of the allowed energies for the infinite square well, and t that we would like to end up our discussion here.